Hi, in this video I'm going to show how to use the gpucoder.stencilKernel function to accelerate the neighbor processing pattern or stencil pattern that is used in the game of life example shown here. Game of life is basically a basic simulation of cell reproduction based on a set of very basic rules. And basically you start, at least in this example, with a matrix of random cells, and then we're going to apply 100 times these rules and see how which patterns occur. The patterns are going to be simple, so we're going to start with this simple a random number of cells, and then eventually we're gonna get here. And you can see offline the game of life, and you will see that if you run this for a long time, you're gonna see some interesting patterns. But we are just gonna run it 100 times just to show how the GPU coder stencil kernel from the GPU coder toolbox of MATLAB is able to accelerate this pattern. Okay, the neighbor processing pattern is important for applications like deep learning. For example, when you are going to recognize an object within an image, usually you use a convolutional neural network, which has a bunch of convolutional layers that make expensive computations on tensors. These operations are convolution, which is a neighbor processing operation in which you have a window, and the output of the tensor, of the element of the tensor, depends on the neighbors. Same thing in image processing, for example, morphology, delayed, erode, or IM filter from the image processing toolbox from MATLAB. The output pixel of the matrix of the image is depending on the corresponding input pixel plus some formula on the neighbors. Also, you see this in finite element analysis for structural analysis, or fluid analysis for turbines, or weather analysis, in which the forces, acceleration, velocity of an element depends on the neighbor elements. So in all of these examples I mentioned, the computations are very expensive on tensor data, matrix data, which a very large amount of elements. So the parallelization is important in these computations to make them practical, and especially the GPU helps in this because you have so many processors executing at the same time. So a GPU makes them even more affordable. So we're going to see in this example how the GPU coder from MATLAB, specifically the GPU coder stencil kernel function, is able to accelerate this pattern. Okay, so let's get there. But before, I'm going to show the rules. The rules for the reproduction of cells is very simple. If there are 3 neighbors, the cell comes to life. Or if you're alive and you have 3 cells, also you remain alive. If you're alive and you have 2 cells, you stay alive. If you have more than 3 cells, you're overcrowded and you're gonna die. If you have less than 2, then it's lonely and it dies. Okay, so those are the rules. Okay, so you click here and just have it open already. So I'm gonna go there. Okay, I'm gonna delete this codegen folder. Okay, I'm gonna run the example. The grid is gonna be 500 by 500 like this one, and we're gonna use 100 iterations. Okay, so we're gonna create a random matrix 500 by 500 with 75% probability of not being alive. So we're gonna have a Boolean matrix, so where 0 means that the cell is not alive and 1 means that it is alive. Okay, let's display it. Okay, so this is the initial matrix. Those are the cells that are alive, the ones in green. Okay, now let's execute the original algorithm. This is the original algorithm. These are the 100 iterations. The initial grid is copied into a temporary grid because it's going to be updated for each of the 100 generations. And for each of these iterations, we're going to execute this algorithm. And what this is going to do is going to create another matrix based on the input matrix. We're going to create another neighbors matrix that is going to compute for each element the total number of neighbors that it has, because that's what the only thing that matters in the rules, how many neighbors you have. So in this computation, you don't have the center pixel, you only have the neighbors. Okay, to get the neighbors, we have to shift the indexes. So that's why we use P. And P is the indexes that are shifted to the right, so we get the left neighbors if you use it in the column. So because there's no zero element, we have to repeat the first element, and then we shift to the left to get the right elements. And again, there's no n plus 1, so we repeat n as the final element. And so we get the left elements, we get the right elements, we get the upper elements because we use it in the first dimension now, and then we get the lower elements. Okay, so now this gets us this, and this, and then we use the same indexes shifting using all the possibilities to get the diagonal ones, which is this one, this one, this one, this one. Okay, we just add everything. There's no center pixel, and we have all the neighbors for each of the elements in the matrix, which are this is going to be the same size. Okay, now this is a vectorized expression in MATLAB, so this comparison is going to apply to each element. So that what this implements the rule of if you are alive already and have two neighbors, you're going to stay alive, or if you have three neighbors, regardless if you're alive or not, you're going to come to life. Otherwise, it's going to be dead. So those are the rules. Good. Okay, so let's run it. And we have this output. This is going to be the output for all the things that we're going to try. There are some little clusters, but we do not run it enough to see interesting patterns. Okay, good. Now let's do the same algorithm using gpucoder.stencilKernel to accelerate it with gpucoder. Okay, so again, we do 100 iterations. We copy the initial matrix to update it. For each iteration we update it, and the gpucoder.stencilKernel, what it's going to do, it's going to run a window through each element in the input matrix in this, and the window is going to be 3 by 3. It is 3 by 3 because that's how the rules are defined for this game. You have 3 by 3 window, and this window is going to be passed through all the image like this. So you're going to go out of bounds at some points. And the same way that we handle the out of bounds case by repeating this edge in here, the gpucoder.stencilKernel with this rule is going to handle it so that the output grid is going to be the same size as the input by specifying this. Okay, so the window is going to be 3 by 3, and this callback function is going to be executed for each window in the iteration that this one does on the matrix. So this is the current window. It's going to be a 3 by 3. So to get the neighbors, we just get the coordinates of all neighbors and add them. Notice that we have a 1 by 1 and the maximum is 3 by 3. This is the maximum, this is the minimum, and the middle one is 2 by 2. And you are not going to see it here because we are not counting the middle pixel, the current pixel, because the current pixel is not a neighbor, so it's not counted. So this is the middle pixel, and it's used to know if the current cell is alive or not. So if it is alive and you have two neighbors, then you stay alive. And again, it's the same rule. Using the counting of the neighbors here. Okay, so let's run it to see how fast it goes. This is gonna take a little while because it's starting the parallel pool, and the first time it starts it's gonna be slower. So I'm gonna pause. Okay, it took 67 seconds because we were starting the pool. So let's run it again. It should take maybe 30 seconds or something like that. I'm gonna pause. Okay, it finished running in 38 seconds. So this is almost 100 times slower than the original function, and you may wonder why we are even bothering doing this operation if it's so much slower. Because the difference is going to be when we generate CUDA code using the GPU coder from MATLAB. But running the algorithm like this has value because we make sure in simulation that the algorithm is working. Because now we can see that the output is basically the same as the original implementation, so we make sure that the algorithm is correct and then go on for code generation. Okay, so let's evaluate it. Let's generate code using the GPU config instead of the regular config that MATLAB Coder uses, and we can run like this. We don't have to use this eval c, and this is gonna give us the CUDA code. We should have the same name of the function, game of life stencil. Okay, so the entry point has the same name of the function, game of life stencil, and you can see that this is the input. When we use this command, we have to pass the input value, which from it you infer the type, which is a Boolean array, and yeah, the configuration of GPU coder config, GPU config. Okay, yeah, so we have 4 kernels. The fourth one is the most important, in which is implementing the sum of neighbors in here, and also the rules. You can see the rules of 3 neighbors here and the rules of 2 neighbors. Okay. Okay, so that's the CUDA code. Now let's take a look at how it executes. Okay, I'm just gonna run it like this. So it took 0.11 seconds. Let's try it again. Oh, this is even faster. Okay, each time is faster for some reason. Okay, let's just pick up this one and compare against the first number. Let's divide it by this one. So we have a speed up of 23. That's a huge speed up of the GPU coder for this example. And the same way that we were able to accelerate the game of life, we can accelerate the training of a convolutional network, and also the prediction. Computing the action values in the network. We can accelerate the image processing algorithms and also finite element analysis. Okay, so the output is the same. Okay, thank you for watching.